So our first few sample problems in Chapter 4 dealt with qualitative aspects of solution chemistry, and then we had a couple of sample problems on precipitation reactions. So where we're moving to now is thinking about acid-base reactions. And acid-base reactions are really important in multiple areas of chemistry. So we're going to spend a little bit of time on it now, but we'll actually have several chapters in Gen Chem 2 that will focus on acid-base chemistry. So it's important to be able to identify if a molecule is an acid or a base. And so table 4.2 is really important. This is the table you need to know because this actually highlights the important strong and weak acids and bases that you need to know. It's important to think about the chemistry that can happen between acids and bases when they react. And then acid-base chemistry is very useful when we're doing titrations. And so you'll spend some time in lab working on titrations, but we'll actually have a problem or two that we'll work through here in our sample problems that will deal with the calculations with titrations. So again, 4 sample problems that we'll work through for this section. The first 2 are relatively straightforward, just kind of having us think about determination of ions in solution, writing equations, thinking about how we depict proton transfer reactions. And then the last problem is fairly involved, finding concentrations of an acid from titration data. So that kind of brings in the stoichiometry component of it from Chapter 3. Okay. So again, first problem here is fairly straightforward. Nitric acid is a major chemical in the fertilizer and explosive industry. So we'd like to know how many H+ ions are in 25.3 milliliters of 1.5 molar nitric acid. Well, again, the first thing, not only is this relevant from Chapter 2, but again, this is one of the strong acids we need to know about. Nitric acid is HNO3. So again, if we have a strong acid, what it means to be a strong acid is it completely dissociates. So strong acids completely dissociate, which means when they are in aqueous solution, they break apart into H+ ions. And in this case, this is what we call a monoprotic acid, meaning it has one hydrogen ion that breaks off. And then we're left with nitrate anions. So we need to know what nitric acid is, that it's a monoprotic acid, and that in being a strong acid, it completely dissociates. We'll actually deal with dissociations of weak acids in Gen Chem 2. It's not anything that we'll deal with in a calculation standpoint in Gen Chem 1. Okay, so again, this monoprotic acid, they tell us that we have 25.3 milliliters of it, and the concentration is 1.4 molar. So hopefully everybody remembers from Chapter 3 that if we're given a volume and a molarity, we can use that to get to moles of HNO3. In this equation that we show the dissociation of a strong acid, that can allow us to walk between moles of HNO3 and moles of H+. And again, the problem asks us how many. When we are counting items, when we're asking about how many, that should be a big clue that we're going to need to use Avogadro's number to get to answer the question of how many H+ ions. Again, molarity will get us to walk between volume and moles. Our balanced chemical equation, which shows the dissociation, will allow us to change who we're talking about, moles of HNO3 versus moles of H+. And since we have moles of H+, we can use Avogadro's number to figure out how many ions that is. So pretty straightforward in terms of a walk, a roadmap, and now our unit conversion that we'll set up. Again, I'm going to start taking shortcuts here because molarity has units of moles per liter. I'm going to convert this right now into liters. And if that's not a unit conversion that you can see in your head, you want to get to the point where you can see it in your head. Just it's going to save us on a step. So we have 0.0253 liters of HNO3. 1 liter of HNO3 has 1.4 moles of HNO3. And so just as a reminder, when we're talking about the concentration of something, it's the concentration of this guy before it breaks apart. And again, the stoichiometry is 1 to 1 to 1, so that will be the same as we have for these, but for other things it won't. For example, if we had a magnesium chloride solution, MgCl2, we'd make twice as many anions. So that'll become relevant as we do some problems in the future here. All right, balanced chemical equation, 1 mole of HNO3 gives us 1 mole of H+. Again, this came from the molarity. This came from our equation. And then Avogadro's number will allow us to take that number of moles of H+ and convert it to actual H+ ions. So this again is Avogadro's number. Mathematically, this works out to 2.1 times 10 to the 22nd H+ ions. Pretty straightforward problem. Again, using unit conversions we've seen previously, molarity, balanced chemical equation, Avogadro's number, but again, just applying it to acids and bases, which we're learning about in Chapter 4.